Hello, everyone. This is Elisa Baum. I'm GridGain Systems Director of Product Marketing. We'll begin in just a moment, but first I need to conduct just a little bit of housekeeping. First, could you please raise your hand located in the GoToWebinar control panel to let me know if you can hear me? And let me see. Oh, great. I see hands. Thank you very much for that. Next, during this webinar, you will be on mute, but should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the discussion, we'll take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain Systems blog. In addition, I will send a link to the recording of this webinar and the slides within 48 hours after the show. And with that said, I'd like to thank you for attending today's webinar. It's a very special joint presentation by Nikita Ivanov. He's GridGain Systems CTO and co-founder, and Jason Stamper. He is a data platforms analyst from 451 Research. And the webinar that you'll be listening today is In-Memory Computing Technologies Now and Tomorrow. And with that said, I'll turn the floor over to Jason. Go ahead, Jason.
Thanks very much. So hello everyone and welcome to this webinar. As mentioned, my name is Jason Stamper. I'm an analyst in data platforms and analytics at 451 Research. So just a very brief background to my company, as you may or may not have heard of us over the years. We're founded in 2000. We're now the fourth largest analyst firm. We just have over 200 employees, over 100 analysts, and many thousands of clients. Now I'm in the data platforms and analytics team. There's 5 of us all together looking at operational databases, transactional databases, in-memory data grids, data integration, data visualization, and more. But of course, across the company, we also have analysts that cover nearly every sector of the information technology landscape, from cloud computing to we do data center verification and infrastructure gradations. We look at mobile, networking, and many more besides. So moving on to the main meat of my discussion then. So I'm talking today about some of the things that we're seeing happening in-memory data platforms and databases in particular. So this is one way that we do. We started off with a kind of tube map or underground map that we then developed into this diagram just for my team as one of the ways that we use to look at some of the customers that me and my colleagues track in the data platforms and analytics space. Of course, most of the focus of today's talk will be around data grids and caches, which just so happens on this diagram to be in the right-hand corner. So I've put a nice red box around it to remind us what we're talking about today. But this just gives you a flavor of some of the areas in which in-memory technologies are being used today. So all of the event and stream processing technologies in the top left need to use in-memory technology in order to be able to very rapidly ingest data and do an analytics and filtering on the fly, and then usually send it off somewhere else, potentially for further analysis down the road or further on, later on. So I put a picture of somebody sort of drinking from a fire hose. I think this is one of the phrases that people use about sort of trying to keep up with some of the feeds that they have on things like Twitter and so on. But of course, it's data coming from all over the place these days, not just Twitter, the other social media, but also sensors, smart devices, and many more. And event and stream processing is one of the ways where in-memory is being used to try and give it that speed, that real-time analytics of some of that data as it's ingested. Of course, many of the analytic databases, not all of them, and data warehouses have used in-memory technology for some time for running those very complicated queries on large data sets. Hadoop you might think of as more of a batch system, and indeed it is. But some companies are using in-memory technologies to sit on top of Hadoop to try and get data from it more rapidly, try and get data out of what some analysts have called the data lake, or depending on how well structured you have it, a data swamp. Operational databases started off mostly as disk-persisted databases, but many of you will have heard that some of the incumbent vendors there have more recently, in the last few years, added more and more in-memory technologies, either as options or added columnar stores that use some in-memory for analytics. And you know who many of the biggest vendors are there. Log management, of course, is a slightly more recent sector. Of course, those operational database companies, some of them, as you know, have CEOs that own islands and jets and things. They started out in the 70s. Log management's a bit more recent, a bit more modern. And many of those use in-memory technologies either at runtime or as they ingest some of that data to try and speed up the analysis of it. And some of the search technologies too do too. And I've put a gold nugget there as that's kind of, to some extent, looking for this piece of information that you might not know you're even looking for, that some of the search technologies can help you to find. And then, of course, perhaps the most important one, well, the most important one for this particular discussion is the in-memory grid and cache companies. But if you don't already know, basically use in-memory technologies to kind of, if you like, slide between applications that you already have in most cases, and in many cases, but not all, databases that you already have, as a way of really speeding up the transactions that your applications are seeing without necessarily having to do a huge amount of work on the underlying databases themselves, which, as you know, are often quite complicated and expensive to change. So one of the reasons that in-memory databases and data technologies such as in-memory grids and fabrics have become so much more valuable and interesting in recent years, of course, memory's been around for many years, is that there's a large gap has emerged between what IT is able to deliver and what the business expects. So many of you who work in IT, I'm sure, will know that many of your business users now consider themselves networking experts because they've set up home Wi-Fi networks. They are business intelligence experts because they know how to use Google or other search engines, and the list goes on. They're mobile experts because they have an iPhone, and they can't understand why some of the technologies that they are given to use in the enterprise or the organization, public sector and government organizations, are not able to deliver the same speed that they've become used to in the consumer IT world. So a survey, for example, by a magazine in the UK of 200 UK-based CIOs, but the results are similar in the US, found that 98% of CIOs believe the gap between what the business expects and what IT and they can deliver is significant. So there's an issue there, and a lot more and more organizations are turning to in-memory type technologies to try and reduce that chasm. In terms of how, of course, as an analyst firm, one of the things we do is we like numbers. So, we track how the different sectors that we cover in data platforms analytics are growing. And this is based on our calculation of where they all were in 2015, and we update this obviously each year. This is the compound aggregate growth rate for the different sectors that we track between 2015 and what we expect them to grow to by 2020. And you'll see there again, a nice handy box for you to focus the eye. You'll see that distributed data grids and caches, such as those we're talking about today predominantly, are seeing very healthy growth. And that's for some of the reasons I've already mentioned, but also partly because this idea of a complete database migration from one database technology to another is not only complicated and expensive, but also carries a great deal of risk because, of course, those databases need to be up 24/7 to handle transactions around the world. So what else is driving some of this change? Of course, we can't forget that it's not just the architectures themselves that are changing with the addition of in-memory. It's also that developers have changed their approaches to developing applications, and that's partly because the applications themselves have had to change. More and more consumers get very frustrated by applications that don't offer good latency. I think the average is around 3 or 4 seconds that if a web page doesn't load, a consumer will abandon a trolley or shopping cart and go to a different website. Everything needs to run very smoothly. And of course, there's also very new kinds of applications that have been developed for things like, obviously the .com and Web 2.0 companies like Facebook and Yahoo and Amazon Web Services and Netflix and Uber have driven a lot of this design change, but also things like online gaming and gambling, social media of different kinds, even internet dating sites and the like have pushed the boundaries as to what's possible for organizations, and that's had a knock-on effect on development and indeed architecture. The other big thing which you will, I'm sure, have heard about is the Internet of Things, and this is an area close to my heart. I write about it from a data platforms perspective, although we also have 6 dedicated IoT analysts in our organization that write about nothing else. So one of the things we do this survey called Voice of the Enterprise, where we survey our many thousands of clients and we ask them about their budgets, which technologies they're finding useful and interesting, any pain points they have, and so on. And so it's our belief, well, it's confirmed by these figures at least, that the Internet of Things is certainly one of the things driving in-memory, because if you ask people about their IoT spending, a lot of people sort of say, oh, well, IoT, it's all hype, it's not a real thing as such. Well, we believe very firmly as an IT organization, and we wouldn't be hiring IoT analysts if we didn't believe it, that it is a real thing, and the investment that we're seeing in IoT is certainly growing. So in this sample, there were 217 people that said they knew what the Internet of Things was. So this is a sample percentage-wise of 217 survey respondents who know what IoT is. And out of those, you'll see in terms of decreasing investment in IoT, which is the bottom three bars, 4%, less than a percent, less than a percent, that actually equates to 11 people out of 217 who are not increasing or keeping their IoT investment levels the same in the next 12 months. And this was conducted late last year. So this is very current data. And of course, it's also the Internet of Things put in place new demands in terms of the speed and volume and variety of data, as we've heard, just like big data is. And it's still relatively immature, but it's certainly changing and maturing and requiring new technologies to prevent data centers and networks from being completely saturated and overwhelmed by some of the data coming from smart meters, sensors, and other smart devices. So one of the ways that we've tried to understand this maturity model is to talk about the machine-to-machine phase, moving towards IoT silos. As many of you know, if you have things like Fitbits and Nike sports equipment, for example, we don't have a true Internet of Things where all of these devices can necessarily talk to one another. They can talk to unnetworked, so we have different networks of things. And we think if we're going to move towards that idea of a true Internet of Things as envisaged when it was first defined, some of these things need to be a bit more commodity, the protocols need to shake out a bit, and we'll see then a bit later on, hopefully, more of a true Internet of Things. But anyway, that's just a view on our Internet of Things coverage. And then 3 use cases when people say, well, IoT isn't real, why do we need IoT? And indeed, why would we need in-memory to help run IoT? So I call that a football because that's kind of a silly joke, really, because I know that's obviously a basketball. But also we have offices in the US as well as in the UK. And of course, in the US, what we call football here in the UK isn't what you call football. However, that is clearly neither a football nor an American football. That's obviously basketball. The reason it's there is because that is a Wilson connected basketball. Some of you will have seen this. You can see on your smartphone how many times it's been bounced, the trajectories. You can start to analyze why you might be missing some of your shots and so on, just because it's got a little sensor in it. It obviously has a small battery in it as well. And when the battery runs out, it's basically just a basketball. It's no longer a smart basketball, but it's still a basketball. And that's been approved for use in professional games in the US and elsewhere. So an interesting and very simple way of using a sensor to get some smart data about things. Volvo's head of connected cars is very interesting. He used to report to the CIO. He now consider it so important to his organization. He now reports directly to the CEO because they think that becoming a more connected car company is one of the ways they need to differentiate themselves. And interestingly, they send data to the Swedish Transport Authority. If, for example, the ABS is deployed, it sends an alert to the Swedish Transport Authority to go and put more grit on the Swedish roads, which obviously freeze very frequently. But also you can do things with your sensors in your connected car, like turn on the heating before you leave the comfort of your own home, defrost your windscreen. If you have an accident and your airbags are deployed, it will phone Volvo, and if they can't get hold of you, they will phone emergency services. So lots of use cases are emerging in those sorts of cars, and of course, when they become self-driving, it become even more interesting. And then the third example is the Samsung Internet of Things fridge freezer range, which not only has a color panel on the front, which tells you things like temperature and has applications you can fit bigger to show you what you'd like to see. I mean, obviously, to some extent, you could buy a cheap tablet and super glue it onto a fridge. But it does more than that. It also has cameras that show you what's inside your fridge freezer. So when you're at the supermarket, you can never be run out of fish fingers and chips or whatever you need in your freezer, because you can see at the touch of a button on your smartphone what is and isn't in it. So again, not all of these things we'll think are hugely important. You can obviously open your fridge freezer before you go to the shops. However, increasingly companies are working out how the Internet of Things might be valuable to their consumers, partners, and indeed their own employees. So an interesting space. But going back to InMemory then, what's coming down the line for InMemory? And I know Nikita at GridGain is going to talk in more detail about some of these, but certainly from our point of view, we're seeing that latency sensitivity concerns are becoming more widespread. There was a point at which real-time technologies were really only used in financial services and to some extent aeronautics and aerospace by NASA and the like, for things like algorithmic trading, very rapid analysis of flight data and so on. More and more, as more applications are online and 24/7, latency sensitivity becomes a concern across the board. We're seeing more and more data platforms that can handle not just operations or transactions versus analytics and data warehousing. We're seeing more and more platforms that can do a mixture of the two. And we think that so that it's almost getting to the stage where you won't have somebody like me that covers operational databases and somebody in my team that covers analytical databases. We'll all be covering all of them because they'll both basically be able to handle both. There may still be some fine tuning that's required. Some might be stronger at some areas than others, but we think being able to do both is becoming increasingly important. To the grid gain area and competition in that space, data grids we're seeing evolve from what was, to some extent, a few years ago, basically a cache between an application and the database into something that's a data platform in its own right, able to handle the things like data center to data center replication, and not being seen as an added layer of complexity, but indeed something that adds additional security and power to your existing data platform setup. We're also, as Nikita will talk about more, seeing new types of memory, which have some of the capabilities of existing memory, but also add some of the better things that disk was able to handle. And as a result of some of these changes, we're also seeing more organizations looking to try and store all of their data in memory instead of just a subset, because of course, although the price of memory has come down, it is still more expensive than disk. So with that, I'll say if you'd like to continue the discussion and you have any questions, obviously raise your hand, use the webinar panel in a moment, but that's my Twitter handle in the meantime. So without further ado, I'd very much like to introduce you now to Nikita Ivanov, who's the CTO and co-founder at GridGain Systems, who's going to talk us through now, as he gets control of his screen, his vision for the next 12 to 24 months as to what he sees happening in the in-memory computing space and data grids and fabric space. So Nikita, over to you.
Thanks, Jason. What I want to talk in the next, probably 20, 25 minutes is basically kind of build on what Jason had talked about in his great introduction, and literally talk about some of the interesting new developments that we see as a vendor across our customers and clients. And GridGain is actually the company behind a hugely popular Apache Ignite project, and we basically provide enterprise version of Apache Ignite. We were original developers of Apache Ignite historically, and that kind of large audience gives us, a fairly interesting view and what actually people are asking us as far as what to develop, where the community is looking in terms of the new features and whatnot. So, but let's begin with a very kind of simple. I want to make sure that everybody on the call sort of on the same page as far as what is actually in-memory computing. We'll keep talking about this technology, but I'm sure intuitively we'll understand it's essentially all about storing data in memory of computers rather than disks. And that's really what it's all about, in very simplistic terms. What I typically try to clarify is that when we talk about in-memory computing, we're not talking about memory only. we predominantly talk about memory first and disk second architectures. It's surprisingly for many newcomers to this field is that in memory computing almost always involves some amount of disk. It's the difference between the disk first architecture of the last 50 years, where we used disk as a predominant system or media of data records, and we used memory, mostly for caching, for simple caching scenarios that, access to RAM is faster, and, if there's some frequently accessed items, why don't we keep them in memory instead of the disk? That was caching, and we used that for literally more than 50 years by now. What in-memory computing brought is kind of flipping this paradigm upside down. We now use memory across many computers in the cluster as the primary system of records, and we use disk predominantly as a backup device. So the functions of these layers, disk and RAM, change completely. But again, when we talk about memory computing, and, as a technology or specific systems that implement this technology, almost always we have some disk involved. So anyways, having that basically squared away, I hope we're on the same page. Let's just jump in and talk about some of the interesting things that we're hearing. And again, there's more things that we do here, but those four that I have on my slides here, sometimes we're hearing, some of them we literally hear almost, if not on a daily basis, but then on a weekly basis for sure. When we talk to our customers, when we answer questions, or look at the questions on the dev list on the Project Ignite projects. The first one is a non-volatile memory. If you follow anyhow any news feeds on the memory or memory computing or new storage systems, you inevitably heard about a non-volatile memory, which is an NVM. The idea is extremely simple. Our current RAM, the DRAM that we have, the DDR4, DDR5 that we have in our systems and video cards and whatnot, if power goes out, the data is lost. It's a very fundamental. That's how RAM was designed, from the early 50s. The non-volatile RAM essentially fixes this problem. It tries to create a RAM, a memory, which doesn't lose its data when the power goes out. So very first implementation of NVRAM was essentially a combination of a normal DRAM and a small flash and a battery. Simple as this. It was basically this convoluted device, and when you power down the system, the battery runs for extra minute or so or extra few seconds to copy the data from RAM into the flash, compress it, and store it in a flash. And when system boots up, there's a certain delay on the boot up, and basically the NVM controller will uncompress and copy data from flash into the RAM. That was it. It was very simple. It was clunky. It wasn't very interesting, but that was essentially what was in the RAM 4 or 5 years ago when the idea just came out. Today, we have much more advanced technology. One of them, probably about the only one that we hear today, is 3DX Point from Intel. That's clearly a proper approach, the right way to do it, and the expectation that in the next 3 to 5 years, the 3DX Point based flash and RAM, because the same technology can be used both for flash devices or flash lock devices and for actual RAM that you can insert in the DIMM sockets in your motherboards. That technology will go up and will be prevalent. What's holding up, obviously, is the firmware, as the controllers, is basically those system level software that we need to all have now, laptops and servers and desktops, to utilize. Obviously, the operating system support, Linux already supports NVRAM pretty nicely, Windows behind, Macs behind. So we need to get all this infrastructure and ecosystem around it. But the non-volatile RAM is here already. We have a number of potential customers who actually are looking for Project Ignite, for example, to support NVM, when we are working on that support as well. And that will fundamentally change how we approach memory computing. Remember, in the very beginning, I said that we always have a disk in the picture. And about the only reason we have a disk, well, there are several reasons, but one of the major reasons is to provide you essentially fault tolerance. RAM, today, RAM is volatile. The power is out, you lose the data. With NVM, obviously that's not true anymore. You can lose the data, you're not going to lose the data. So we can essentially move into the realm of a pure memory computing where you have no disk and have the same guarantees for data reliability and fault tolerance. That's why if you ask almost any analyst and ask him to look literally, let's say, a decade ahead, the external data storage, such as network attached storage or a disk or a flash, will become a little extinct because it will represent pretty much what today tapes represent. If you look around your data center, look around your company, how many tape drives do you see? You can probably find them in some kind of hardcore backup scenarios. This is exactly where you're going to find most of the disk and flash systems that exist today in probably 10 years from now. The NVM is absolutely the last piece of the in-memory computing puzzle. We needed that piece as a community technology to really make the final jump, because as of today, you're still basically handicapped by a need to have the disk somewhere in architecture, to provide you kind of final backup. So bottom line, NVM is absolutely probably the biggest story going on. It's slow moving. It's a very big deal. Not only have to produce completely new silicon, completely new device, you have to produce all the supporting infrastructure for motherboards, for controllers, for system level firmware, for operating systems, but all of it is coming. And once it's there, again, my estimation that we're going to see some modest adoption in the next 3 to 5 years, probably a decade from now. That's going to be the prevalent model of storing data in our computer systems. So something to watch out, and naturally in-memory computing systems is on the front lines. The first real adoption will happen on application level, will happen in something like Apache Ignite or Great Gain or systems like that. Another interesting different angle on in-memory computing is a tremendous growth in machine learning and deep learning. I abbreviated them as ML and DL. That's a typical abbreviation. And it was surprising to me, actually. We have a very interesting project within Apache's Ignite. There is a development of a machine learning and deep learning library, not library, and a feature, an extension that's going to be part of Apache Ignite. And it was actually very interesting to me to learn, why all of a sudden there's a connection between memory computing and machine learning. And if you look at the machine learning, essentially a machine learning on a small, dense data sets, typically something that fits into the memory with storage of one computer, is pretty much a solved problem. There's a tremendous amount of libraries, in the R community, in the Python community, in the Java community, in the Scala community. There's, projects like Spark that solve it very efficiently when the data really fits in the realm of one computer. Spark can do it very effectively within memory and whatnot. But the minute you basically graduate, so to speak, into the large sparse data sets, all of a sudden the problem becomes, there's a step function in the complexity of a problem. There's very few libraries, there's very few solutions that can work on a large scale, sparse big data sets when it comes to machine learning. If I tell you that, I have a 20 terabyte training set for your neural network, there's a very few projects, TensorFlow from Google comes to mind. There's quite a few others, but there are very few comparing to hundreds of projects for a small, dense, kind of a smallish data sets. So, and that's the area I think where in-memory computing is absolutely prime to be a fundamental base technology for the large-scale sparse data sets for machine learning. Because fundamentally, when you think about machine learning, what is the machine learning? Well, it's statistical algorithms, and they work on a large data sets. Well, that must ring the bell, because this is exactly the problem that in-memory computing system and technology solve. In-memory computing allows to store, a large data set in the most effective, most performant medium, which is memory. The whole idea with memory computing is that we can store data somewhere where we can process it with absolute maximum speed and performance that is allowed on that particular hardware. Because when you store data in RAM, there is no other place where you can store the data for a faster processing. It's a very important thought. I want to repeat it again. This is something that, often kind of, escapes our minds, is that in-memory computing in general is not a stopgap solution like Flash was. Everybody knew that Flash was a temporary solution, right? We went from tapes to disk and faster disk, then we went to Flash, which is essentially the same as a disk, but there's no moving parts. But when you move to the memory of a computer, at least in the current, architecture of computers as we know them, think about this. There is no other place where you can move data for a faster processing. Literally, there's no other physical place. So the memory is the last frontier. And that's why we keep saying that when you move to the memory computing, you're literally starting to basically work on the physical on the maximum speed and performance that's physically possible on a given computer and a given architecture. And that's why I'm saying that a lot of people starting to realize that in order to perform a sometimes real-time machine learning on a large sparse data sets, in-memory computing systems for data storage and running the statistical algorithms is about the only option. And I think we're going to start seeing this more and more and more as we kind of graduate our machine learning and deep learning use cases away from simple things and from kind of low-hanging fruits that we, as an industry fairly effectively attacked in the last, 3 to 5 years. As we start graduating to the more complex use cases with larger data sets, with a lot more complex training, we're going to start to see a need for a in-memory computing based machine learning, because this is the only way where you can have tens of terabytes of training data and have any hope for any kind of fast processing of this data or fast learning, or essentially applying those models to real streaming data. So bottom line, my belief, and that's not only my belief, if you look around the community, there's just tremendous interest in what we do in Apache Ignite in terms of the machine learning rate. The machine learning and deep learning is kind of, part of much the same kind of idea. Will become one of the major use case when it comes to applicability in memory computing to the businesses. Moving onward, this is another interesting sort of discussion points, and that's something that we at GridGain specifically heard many times. Essentially, the conversation typically goes exactly what we say here. What I say here on a slide is typically our customer would ask us, "Okay, guys, but can you support petabytes of data?" And because, for example, we heard that Hadoop can support petabytes of data. Well, nobody really does, but it can. And our typical answer, 3 or 4 years ago, would be no. Petabytes of RAM is just impractical. It's way too expensive still today, and it's just impractical because you will have to have thousands of computers in the cluster, and it just apart from very specific use cases in government and military, it's just impractical. But then things started to change because the questions like that 10 years ago were very few apart. It was mostly theoretical discussions. And in the last couple of years, we were asked not about petabytes, but we were routinely asked about tens of terabytes. And if you think about it, what is what is the let's say 128 terabyte of RAM? Well, it's a fairly significant amount. You really have to have a small data center for that amount of RAM to be in a system. And we basically needed to find an answer for this question. What's also interesting, by the way, that in the same time, as we were solving this problem, and I'll explain how, I think I explain why it's interesting and important, there is also a movement in the verticalized systems. And I just giving you one example here is that Fujitsu, for example, has an M10 system, which is essentially a very large Solaris system that has 64 terabyte of RAM on one server. Now think about this. This system is shipping today. You can buy today. It's fairly expensive, but you can buy today. You can buy a massive server with, I don't remember how many, I think it's 512 CPUs and 64 terabyte of RAM. Let me repeat it again, 64 terabyte of addressable RAM, normal RAM, that you can basically have on one server. So this is rapidly changing. Obviously, it's expensive. It's a one-off computer. You're not going to buy this, on a whim. But nonetheless, that's existing and shipping today. But nonetheless, we've been asked about it, and I believe when we ask our customers back why you're asking about it, they gave us plenty of reasons. And many of those reasons essentially is that the usage of in-memory computing systems really has matured in the last, I would say, decade. As Jason mentioned in the very early, the in-memory computing was all predominantly about caching, very simple caching. It was local caching, distributed caching, but it was just the caching. And in the last decade, slowly, gradually, what has happened is that in-memory computing rapidly becoming a predominant paradigm for system of records. I would say that across our clients at GridGain, roughly, I would say probably 60 to 70% of our users, or maybe half, just to be safe, use our software as a system of records. Think about it. This is where people keep all their records as they would in database. Maybe it's because our system supports full SQL and whatnot. So we have lots of technology to really accommodate this use case. But nonetheless, people do choose in-memory computing systems as the system of records, and they use disk or existing databases predominantly as a backup devices. But when you graduate to this use case, you naturally start asking about the capacity, because in many cases, maybe you don't have 20 terabytes today, but when you choose a system, you want to make sure that system can support in the future large data sets. And then we started to hear these questions from our customers. Okay, can you guys support this and that? And I think where the technology is moving, and we know that from our perspective, from our couple of competitors' perspective, we're all moving what's called a hybrid storage model. We all sort of realizing that asking our customers to have, which means buy, terabytes and terabytes and terabytes of DRAM, it's probably not a good option. So what we developed essentially in Apache Ignite, as a community in Apache Ignite, we developed a hybrid storage model where we provide a universal interface to either RAM or flash or spinning disk. And we allow basically you to not know the details where your data is stored. And we'll give you the full unified API to it, whether it's a key value access, compute grade, or a SQL. You don't know where your data is. We obviously, on the background, will move data to the fastest layer, which is RAM or flash, or essentially we're gonna favor the speed versus capacity. But once the RAM is saturated, we're gonna we're gonna store more data in flash and then more data on the disk as flash is out. In this way, you get the system that operates exactly the same way. You don't have to know where your data is located, disk or flash or RAM. It works exactly the same way. But the more RAM you have in your cluster, the faster your system works in general. The less RAM you have, the cheaper it goes, but it works slower. It's a very fine balance where you can basically can literally regulate the speed of system you develop with this particular technology by simply adding RAM, which is a little bit more expensive than a disk. So you can spend more, add more RAM, get a lot more speed, or it can be very economical, work predominantly with a flash and disk. System will work slower, somewhat, obviously, because flash is nowhere near as speed as RAM, but you're going to save economically. So surprisingly, all of this may sound like fairly vanilla technology, but it's not. It took us a number of years to really to develop this technology, because the biggest problem and difference is that the RAM is byte addressable, and most of the algorithms within Apache Ignite has been optimized with byte addressability, and while the flash disk is a block level device, and the differences are dramatic. As you can imagine, when When you're reading the 1 byte from a disk or flash, you have to read the entire block of data and use only 1 byte. There's a lot of waste in this. But when you read the 1 byte from RAM, you read 1 byte of RAM. There's no waste. And there's obviously a catastrophic difference in terms of latencies, right? The RAM is nanoseconds, and your flash and disk typically in milliseconds. To really reconcile all these different storage mediums, it was a pretty hard job, and that's why there's only a few projects in the world that actually successfully solved that particular problem. Apache Ignite is one of them. I think the community will ship somewhere in the next 60 to 90 days that feature. And we know for a fact that this is basically, it's been worked on by quite a few other projects as well, because this is the logical next wave where a memory computing system will go for. Yet another interesting kind of a use case and maybe discussion point again is all about SQL. If you remember, if you've been in the Silicon Valley or been in the in a data processing community, about 10 years ago, the narrative sort of on the street was a SQL is dead because everything is going to be NoSQL. Nobody needs complexity with SQL. Nobody needs all these constraints. Just schema-less data. We're all going to go a NoSQL route. And there was abundance of new databases that support, kind of eventual transactions and different ways to query data, different ways to store data. And eventually, as many would have predicted, we came back to the same idea that, oh my God, SQL is still basically a #1 paradigm for data processing. And there's many reasons for that. There is, I don't want to really negate all of this, but there's a tremendous amount of reasons. There's, millions of people familiar with SQL. One of the fundamental features of SQL is indexing. So when you don't have a key, you need to basically find something with, with a scan. If you don't have a SQL or indices, you're basically doing a full scan, which is horrific performance-wise. And, literally, another part of a SQL is that, again, the story goes that as use cases of in-memory systems becoming more and more complex, people need more and more complexity on querying this data, right? It's no longer just a key value access. You have to query. You have to have a complex aggregation functions, joins. You have to be able to basically do fairly complex querying on this data, because that's what your use cases are, business use cases are. And I think it's a part of a theme as in-memory computing use cases mature and mature more. We started to hear about 3 to 4 years ago that SQL is becoming literally kind of a necessary part of that, because we were basically asked by customers, how do we do this? How do we do that? How do we query this data? Why do we have to do so many setups to do a very simple thing when in SQL you can do it with one line of code? And when we heard that many times, we actually decided to basically add a first-class support of SQL. And now essentially that's, if you look across memory computing, if you look across Hadoop, look across any other significant data processing projects or technology, SQL processing become an absolute necessity. And I do believe that going forward, there'll be no serious IMC vendor or a project that would not have a SQL access or SQL capabilities. And I'm talking about truly SQL capabilities, because before that we were toying with ideas, well, why don't we develop our own query language? And if some of you may remember, something like 5-7 years ago, there was a whole kind of interest in developing that every project would develop its own query language. We kind of moved away from that because nobody has any time or desire to learn yet another query language when we have SQL that's been matured for the last, 40, 45 years by now. And I think as the industry, we come into a fairly, obvious realization that SQL is the king over data processing, over data querying at least. And, any serious in-memory computing system would have to have first-class support for SQL. If it doesn't have it, it literally has no chance. in this new, more complex, more serious use cases for memory computing. So we have it, when I say we, Apache Ignite, again, some other projects have it too. Spark has SQL support. Hadoop has the whole small cottage, industry of the SQL support for Hadoop systems, and that's basically just the same. It's basically manifestation of the same trend. Okay, I believe that is the last of my slide on my side. I want to go back to Elisa because we have this conference that we're going to be hosting. Not us, but we are organizing it in Amsterdam. Elisa will have some couple of words about that.
Okay, before we get to our questions and answers, by the way, thank you, Nikita and Jason. I'd like to offer all attendees here a special offer for the InMemory Computing Summit, which is happening in Amsterdam, June 20th and 21st. It's going to be the very first InMemory Computing Summit in Europe. So this is going to be a premier event. We have over 30 breakout sessions from all the leading vendors of in-memory computing technologies, as well as some of the top users, learn about their use cases and learn how what they're doing can help you. I'd like to tell you that we have a special rate, early bird rate that ends on the 21st. The early bird rates are 10% off the normal registration price. But I'd like to also give you guys an additional 10% off of that with the webinar registration code of webinar IMCS. You'll see that there. So if you would like to attend, this special offer gives you 20% total discount. And it's a great way for you to really get in there and learn all about what's going on in the industry. Both Nikita and Jason should be there. So you'll get a chance to talk to them as well. All right, with that said, I'm going to turn the floor over to questions and answers. And if you do have any questions, please go ahead and enter them in the questions panel within the GoToWebinar control panel. Okay, so the first question, what is Spark SQL good for versus what is GridGain with SQL good for?
Yes, so I would say basically the fundamental difference will be speed. And again, when I say that, it doesn't mean that Spark somehow has a bad engineering. Spark was never designed for a fast SQL. Up until recently, I think they, I don't know if it right now, but they never had indices, for example, or properly implemented. It's very true because it's very hard to implement indices in RDDs. I don't know what the status for this right now, but about 6 months ago, we were outperforming Spark SQL by 2 orders of magnitude. So it was very, very different performance. And again, not because we're somehow smarter than those guys. We have a huge respect for Spark community. It was basically, it's an architectural issue. It's very easy for us to have proper indices, and we have very strong SQL engine for this. And Spark never had this because it's literally hard to do. So fundamentally, the difference between Spark SQL and Ignite SQL will be a dramatic speed performance difference.
Okay, great. The next question, I'm thinking this is for Nikita. How much will I have to rewrite my applications if I adopt Apache Ignite or GridGain? I am currently using older versions of Oracle and some SQL Server.
It depends. Let me answer this in 2 ways. Just on the numbers, we've seen adoption of GridGain, forget about GridGain, Apache Ignite, adoption of Apache Ignite in a heavily SQL projects going anywhere from few days to half a year. So it massively depends on whether you use a lot of store procedures, because store procedures will have to be rewritten in Java, for example. But if you only use SQL 99 and you stick to SQL 99, we actually shipping GDBC, ODBC drivers with Apache Ignite. And you can literally use that. So if you're a SQL 99 straight out, your entire integration can be literally a few days exercise. If you're a heavy user of store procedures and a proprietary extensions from Oracle, that can take a while. You cannot change the laws of physics. So it's anywhere from literally a few days to it could be stretched into the months and months and months of work.
Okay, next question. With this new RAM to disk functionality, can I now use Ignite as a long-term data store instead of, say, Cassandra?
Yes, Cassandra is an interesting comparative use case. Cassandra's great advantage is scalability, uh, which is exactly what we do as well. But unlike Cassandra, we're not limiting you to a non-transactional or proprietary query capabilities. We first of all, we are dramatically faster than Cassandra because again, it's when I say this, comparative, statements, it in no mean I'm saying that we're somehow smarter or better. We're just architecturally very different. Cassandra is a disk-based system. So naturally, any in-memory computer system will outperform it by several orders of magnitude. So we're dramatically faster. We can scale up to 1,000 nodes. So unlike many other in-memory systems, we don't have the deficiency in terms of scale compared to Cassandra, because one of the strongest Cassandra point is the massive scalability and parallelization that Cassandra brings. We can do the same, but I believe we add a lot more. We add full SQL support. We add full normal transactions to it. We add all the streaming capabilities. We had all the compute grid capabilities. We have all the machine learning capabilities. So we just have, a lot more than just, a typical Cassandra would give you. So we've seen a lot of use cases where people migrating from Cassandra either to Ignite or adding Ignite on top of Cassandra to add, query and transactional capabilities on top of the Cassandra as well. Because again, Ignite can actually be used, and we see a lot in the community, by the way, as this kind of high performance layer on top of the Cassandra. And that's, very interesting use case as well.
Okay, next question. Does the latest version support all of H2 functions?
Do not know. This question is correct that we use H2 as the localized SQL engine. I really advise you just post this question on the dev list for Apache. Somebody will jump on within half an hour will answer this. I do not know if we support all of them or not.
Okay, I think this one is for you, Jason. You said that the Internet of Things is one of the drivers for in-memory technologies such as grids. Why is that? And then there's another comment. Surely the data from sensors is small in volume and easy to analyze.
Yeah, excellent question. A lot of the data that comes from smart devices, sensors, logs, and the like, it tends to be, as the questioner quite rightly said, in smallish packets. Unfortunately, they're often in very different formats from one another, which is a different question about protocols and integration, but they do tend to be in relatively small packets. However, I think I touched on this briefly. Just a Formula One car these days has 300 sensors. I know of a company that puts sensors on trains to try and improve their efficiency and their braking and so on. They currently have 400 sensors on each train, and they think that in the next 5 years, that is more likely to be 4,000 sensors. And also, if these sensors are taking readings, let's say every millisecond, the amount of data can very quickly add up to very large volumes of data. And that's where, as Nikita's been explaining, in-memory technologies have a real advantage in terms of the pace and performance with which they're able to analyze very rapidly large amounts of data. Even if it starts off in small packets, you then need to correlate, find anomalies and patterns in that data, and possibly run machine learning over it as well.
Okay,
Nikita, did you have anything to add, or is that think you addressed the question? Do you have your?
No, I think Jason said it perfectly. Yeah, just generally, I would just completely echo what Jason saying is that if you kind of step up from a technology to kind of business use cases, IoT is a massive driver, and that's a very ideal fit for memory computing. Lots of data, streaming data, latency is absolutely critical, and literally, if you're in engineering, think about it. If you have the avalanche of data, in the Volvo cars is a perfect example. You're not going to be doing this on the disk databases. It doesn't work this way. No matter what you do, you'll end up doing something with the memory, because this is the only way you can have a workable system today and something that you will not have to redevelop in 3 to 4 years. So in-memory computing is literally about the only technological choice today for a kind of new crop of IoT systems.
Okay, I think we've got time for one more question, and this is a follow-up question on the Cassandra question that you answered, Nikita. My main point was whether I can now use GridGain as my only database, including long-term storage.
Yes. The answer is yes, and I'm not going to pretend we have all the tooling and all the ecosystem of somebody like Oracle or Microsoft SQL, but this is inevitably where the in-memory computing systems, and specifically Apache Ignite and specifically GridGain system, is moving to. I mean, again, that's predominantly driven by the demand from our customers. They are moving into these use cases, and they're basically forcing us to co-develop with them, if you will, all these features and all this ecosystem of tooling. Like things like backups, for example. 10 years ago, this thought never would cross our minds. Why would anybody need a backup for cache? The cache is already the data already exists somewhere. We're just caching. But today, the backup of in-memory system is a very important feature, because naturally when you start using the memory system as a system of records, you want to back it up somewhere, whether it's a data center application, where it's actually a disk backup for historical and just backup reasons, and then when there's a backup, there's a whole complex in terms of backup. Is it a full backup? Is it a delta backup? Is it a basically incremental backup? There's plenty of this a satellite issues around the core technology that's starting to popping up, because the use cases, again, becoming more and more complex and more sophisticated.
Okay, great. I think that's it for questions today. I wanted to thank the audience for attending our session, and also Nikita and Jason, thank you for a great discussion. I will be sending out a link to the slides as well as the recording within the next 48 hours. And with that said, I'd like to thank everyone again for attending our webinar. I hope to see you on future shows. Jason, Nikita, thanks again.
Thank you. Cheerio, everybody.
Thanks a lot, guys. Bye-bye.